Yo, what is up, everyone? Hello, sup, beautiful bastards. I am back. I am back to something I haven't done in a very, very, very long time. I am doing a quick little study session because I just think this problem is literally just so insane. I just wanted to showcase what I've been doing personally in my life whenever I'm not streaming. And it's this stuff. Studying. I have an exam next week for this class. It's actually insane, this class. He gave us a problem that is going to be on it. It's this problem. But it's reversed where I'll explain it. But this is the problem that's going to be on the exam. And we're going to go through it today. And I know, I'm aware I did get banned. I was stupid. I was drunk. I'm aware of the consequences. I won't make a mistake like that again. I was stupid. So, that's that. I shouldn't be really reckless when it comes to that kind of stuff because this is my channel I should be thinking about. Although I don't really care about streaming, I do want to preserve the channel itself and the history behind it. And all I've done in the last like 3.5 years. So there's that. But back to the problem. We're gonna do this problem today, and then we're gonna maybe play like a game of Geo or two. I want to try to do maybe a duel or two, and then we'll probably call it a stream there. I may be live later, and well, I don't know if I'll be live later. Probably not. So let's just get right to it and get this baby started. So, this is the problem that's going to be on the exam. The class is called, no one's going to understand anything. This is literally graduate level engineering. So I'm not going to go out of my way to explain literally everything, but I feel this way of studying really helps me. Like, I did this about 2 years ago for 2 of my classes, which I was really struggling with. And one of them happened to be also fluid mechanics. This is not fluid mechanics, but it is fluid mechanics. It's like a more in-depth fluid mechanics class of a certain sector of fluid mechanics. Heat transfer, fluid mechanics. But, I did this about 2 years ago for my fluid mechanics class, and for my, I think it was design. I think it was like a design class, design of machine elements, I think. And it really helped me study. And that was back when, probably right before I started Geo. So I really wasn't, I was kind of just experimenting with a lot of stuff because I just got, I was just streaming on started streaming on the computer. It wasn't my computer, it was my brother's at the time. But, and I started experimenting with stuff and I was like, you know what, let's do a study stream because I was studying and I was like, fuck it. So I did a study stream, it helped me a lot with studying, but no one really fucking cared. It's boring. This is graduate level stuff though, so it's pretty complex, so maybe it'll be more interesting for people. But if you hop in, you could just chill out and you can, I know most people that go to Twitch aren't really looking to learn education wise, but this is free education right here, graduate level education right here. I don't know if there's a category for education. Is there? There is. It's 5 viewers though. We're gonna just do just chatting. Hopefully everyone's weekends were good, weeks. It's been a while since I've actually done a full stream. The stream ended really fucking short yesterday. Friday. Ended really short Friday. So I didn't really get to talk much, but let's get right to this problem and stop wasting any more time. So this is the problem. It's convective heat transfer class. So this is a flat plate right here. And so this is the problem, okay? So you have a flat plate. And on this flat plate, it's kind of like wet. Well, it's actually really wet. It's like a very porous solid, okay, that you have here. This plate is. So like, imagine you have like a plank of wood, and it's really wet, like a sponge, a long sponge. So you have this long sponge right here. This is the sponge. It's fixed to the ground, or fixed to wherever. And basically, there's air that's going to be rushing over the sponge. And when you have air rushing over a sponge in a laminar fashion, this is a laminar boundary layer. It creates that, which is this. It's the laminar boundary layer. And basically, this T infinity is the temperature of the room. It's like the room temperature. This is the temperature on the sponge. And then this is basically the height of this boundary layer that forms from the air rushing over. And this U infinity is the constant air above this layer. U infinity actually is just like the speed of the air outside, but U changes a lot in this boundary layer. After the boundary layer, it stays the same. It's just a constant, but through this boundary layer, it changes a lot. So that's like the terms. This is the y direction. X will be here, and X is assumed in this problem to be large, very large. So it's a very large sponge that goes on forever, basically, indefinitely. So a lot of things can be assumed from that. And also, with the sponge, basically, we're going to be sucking fluid out of the sponge. That's what this is. So at a certain velocity, it's called velocity VO. So you're sucking this fluid out at a velocity VO. You have this height of the boundary layer. You have the temperature on the sponge. And you have the room temperature, which is T infinity. And then the speed outside of that, which is just U infinity. And it's going to be steady flow with constant fluid properties. That's basically saying that all the properties of air, which is flowing over this, should probably put that air. This is air that's flowing on top of here. They're basically going to be constant, which doesn't really... That basically just makes the problem a bit simpler. In the no-slip condition, it helps with one of the boundary conditions for the problem. And this is basically... I can't type it out, but this is what this is right here. This is... It's called tau, which is the shear stress. That's the shear stress next to the sponge, the wet plate. It's called T sub W, tau sub W. And basically that is dynamic viscosity, or mu, over d sub u, which is a component of velocity. So there's like a x and y component of velocity, like vectors, if you know what that is. So there's an x direction and a y direction, so velocities can be angled in the x and y direction. So that's what u, and the other one is v. Those are components of velocity. So that's d sub u over d sub y. It's a partial derivative at the wall. That's what that's saying. And basically, these are just assuming a lot of properties that, like, the velocity ends at the sponge, That's what some of this is saying too. So you could assume that. This is for one of the boundary conditions. And isothermal means that just on the sponge, it doesn't change. It's only T sub W on the sponge. It doesn't, there's no different changes in temperatures on the sponge. It's the same temperature from this part of the sponge to that part of the sponge. Okay, so now that's out of the way. That's kind of the introduction to this problem. A laminar boundary layer, which means basically there's laminar and turbulent. Turbulent is very confusing, and even graduate level classes don't really delve into that as much until that's more like late. But it's most graduate level classes would not do that for an exam because it takes way too long. Because when it's turbulent, there's a time factor into it, and it gets really confusing. Laminar is very simple. It makes the problem a bit just, you know, easier to do in a session. So yeah, again, we have this sponge. It's a very wet plate, and we're suctioning out this fluid out of this sponge at a certain velocity while air is rushing over the sponge and creating a laminar boundary layer with a constant temperature on the sponge, T sub W, and an air temperature, T sub infinity, and a constant velocity, U sub infinity, after the boundary layer. Before the boundary layer, this is kind of what the this is kind of what it looks like. This is the velocity. So there's a temperature boundary layer and a velocity boundary layer. This is the velocity boundary layer. So this is basically what the speed distribution kind of looks like. And this is U sub y, which we're finding in this problem. I'm gonna guess in the problem, I think the temperature boundary layer height equals the temperature, because there's lambda and then there's lambda T, which is the temperature. I don't think we have to worry about that as much, but I'm gonna just think that is what the problem has. It doesn't play much of a factor into it. So for this problem, we are going to find the basically the use of this equation right here, and we're also going to find the equation for T sub y, so the temperature one, which is, let me draw that up real quick. I don't want to mess up the drawing. It's a little bit different than the velocity one. Un momento. I'm gonna. Actually, let me look at my notes. There it is. Kind of like this. Not really any lines, just like this is the line. So we're finding T sub y and U sub y. that's kind of like the main thing. These are the two main things that we're finding in the problem. After that, this stuff you can find from these equations. So from here, you can easily go from here. From here, you can easily go from here. And you're assuming a large X, which basically means the partial in the X direction, so partial of U over partial of X equals 0. That's what you can assume from that. Because it's so big that it's just, you just take it out, basically. A big old goose egg. So, let me move my camera. So basically from that, you can assume, we'll get into it when we get to the first one. We're just making the, wait a minute. The first part of the problem, we're just making the continuity equations and basically the equations we're going to be using in the problem. That's what we're doing in the first part, and finding the temperature and velocity distribution on this boundary layer. So, with that in mind, let's get right to it. So we're gonna have this second part kind of like right here. I know it's gonna be kind of like disorienting, but we'll go with it. All right, so there are 3 different big equations that we use in graduate level fluid mechanics. 3 different equations, okay? So one is the continuity equation, which basically means it's a conservation of mass. So it basically means the mass going in an object equals the mass going out of an object. That's what that basically means. So if I entered into this room and flow and exit this room, I'm gonna weigh the same amount. That's what that means. And the equation for that, and again, there's 3 different components for velocity. Velocity is a vector. There's u, little u. There's v, little v. That's j. And then there's also w, which is z. This is 2D. Where does it say 2D? 2D. So that means only x and y directions. But we're going to write out the entire thing, and we'll cancel out everything, because that's what I'm going to have to do for the exam. So I'm just going to go ahead, do the entire big equation. It's a big equation for 2 of them. And we'll go from there. Actually, I'm going to actually find the big equation for, because I did this problem once before, and the other time I did this, I kind of just skipped that part. But for the exam, we're going to have to go from the simple equation, like the big, long equation, and cancel out everything that needs to be canceled. And basically write that out. So I'm going to go do that as well. So, air is an incompressible fluid. Oh my god. We're assuming density's constant in all different... The density of a fluid is constant. And we're also assuming in this problem that... What else was I going to say? Oh, air is an incompressible fluid. So there's compressible fluids and incompressible. A compressible fluid would be water. That's what a compressible fluid would be. Because, yeah, basically gases. Most gases are incompressible. And air is a gas. So, incompressible fluid. So a lot of things could be canceled out from all the equations from that. Okay. Just had to get that out of the way. Let's get to it. I'm going to move this up a little bit. Okay, so we have this with the large X. That's something to think about as well. So, the first one is the continuity equation. Basically means conservation of mass, as I said before. That equation lengthened out. It's a bit lengthy. Actually, this is the least lengthy one. So it's basically the density over time. This is laminar, so we don't have to worry about time. Laminar. So time is not a factor. Should put that. D over d sub t, partial over partial t, equals 0. It's big. That's really big. So it's partial phi over partial t plus, what is it, Bant? What do you mean 7? So this is it lengthened out. So you got phi times u over d sub x plus d phi sub v over d sub y plus partial phi w over z, and that's all equal to 0. You want a tourney from cheating? All right. What tourney was this for? Can Congratulations. I don't know how you want an Applebee's gift card or something? So this could be canceled out because of the laminar. And since V's constant, density's constant, we can just bring density out and just cancel out density and divide it out. We also are in 2D, so we can cancel out that. And that just leaves us with partial u over partial x plus partial v over partial y equals 0. That's the first equation. And we also assumed this is 0, so we can cancel out this. So, basically that means d sub v... Actually, I'm going to keep... Oh. I'm going to keep this in. But since that equals 0, you want 20 bucks? Hell yeah, go to McDonald's. I gotta do this. I'm doing this problem. You can learn something, Vamp. It's very interesting. I'll explain it one more time. But you probably don't even fucking care. But basically you have air going over the sponge. I don't think they're working. That's honestly good. I don't want it to interrupt. Alright, let me get back to this, okay? So basically that means a partial of v over partial of y. Well. Oh my fucking god! There we go. Basically that means this little v equals v sub o, which is basically the rate at which it's suctioning out this fluid from the sponge, which is the plate in this case. And that non-slip condition, this is what that means. A non-slip means like at y equals 0, at y equals 0, that's y, on the sponge, u, which is a component of velocity, equals v, which is a component of velocity, equals 0. That's what that means. And that's the only boundary condition for this one. So that's the first equation. Now I am going to move this slightly more up. Alright, the next one is momentum. So it's a pretty simple physics thing, alright? You know what momentum is, right? Mass times velocity at one point equals the mass times velocity at another point. Basically, that's what that means. Logistically. And this is the conservation of momentum of a fluid. It's really, really long and really confusing. So I'm just gonna write it out first. And then I'll explain. So, just so you guys know, that's density, okay? I'm gonna write a little f of x. I'm gonna do that down here. Little f of x is like just the force. And this is just, I'm gonna just write the x direction. This is kinematic viscosity, which is viscosity of a fluid is basically just, there's viscous flow, and then that's really about only the other basic flow there is. I mean, non-viscous flow. There's viscous flow and non-viscous flow. That's what there is. It's basically the type of flow. Okay. Mu, which is this right here, that is dynamic viscosity. That's shear stress. That's what it says there. This is shear stress. I'm actually not gonna write it all out because it's really fucking long. I'm gonna write the simpled out version because this is gonna take fucking a long ass goddamn time for me to explain every little fucking thing. Because this is gonna get really fucking long. So I'm just gonna write it out. Because I already know what needs to be canceled out and everything. It's not hard. So I'm just gonna skip that. That's all you need to know. So this is what it comes out to be when you cancel out, you know. It's two-dimensional, so x, y. And incompressible fluid, non-slip, uniform free stream, all those conditions, this is what it comes out. So u, small u, this is a component of velocity. Over that same thing over x. Also, did I? It's minus. This is negative. The reason why this is negative, by the way, this is the rate at which it's suctioning out, the velocity it's suctioning out this fluid out of the sponge, is because it's coming out of the sponge. If you're putting stuff into it, injecting fluid, it'd be positive, but we're taking stuff out in this case. So this little v, which is a component of velocity, is equal to this rate, negative, because it's coming out. So that plus v over d sub v over d sub y equals that kinematic viscosity times, oh fuck, I'm pressing the wrong fucking one. D partial squared of u over partial y squared at w, which is y equals 0. And so this could be rewritten with the, since this is equal to v sub o, you can rewrite that with minus v sub o. So That's big. And this could be canceled out. I might as well just do that now. So this U is going to be equal to 0. So that's going to be this equal to this, which is, that's basically the main step that gets us to the, I'll just break it to you. The momentum's going to give us to the velocity distribution, and there's going to be another one after this called the energy equation, which is basically the conservation of energy of fluids, and that's going to help find the temperature distribution. So I'm going to write out the boundary conditions, and the boundary conditions for this are y equals 0, U is going to be equal to U infinity, which is that constant. You see how it meets the plate at x equals 0? This is basically where U infinity starts. So at x equals 0, it meets it, so that's why that is there. And then also, actually, at y approaches infinity, which is basically just y approaches past this laminar boundary layer. Oh, this is at y equals 0, by the way. This only occurs at y equals 0. Which is why that is done, basically. Okay. All U also equals U infinity. Okay. And then we got the energy. I'm gonna write that one out really quickly. The energy equation is kind of like the same format as this one. You have U d sub t over t sub u, plus v over d sub t over d sub, or wait, this is x, this is y, equals, so this would usually be, it's k over phi cp. This is usually multiplied by phi and cp, and cp is like the, what's the word for that? K is the convective heat transfer coefficient, which basically is the heat transfer rate for convective terms. And then CP is like for gases, it's a constant property for them. That's what that is. So it's K over phi CP, which that is equal to alpha, which is called thermal dissolutivity. This basically thermal dissolutivity or whatever. Dissolutivity. is the rate at which a solid increases its length or decreases its length in terms of temperature. Because if you don't know, when it gets colder, stuff gets smaller. And when it gets hotter, stuff gets bigger by a very small amount. But this is the factor for that. And it's equal to that K value over phi Cp. So that's what's that's what that is. This. So you could just put alpha there. But I'm just gonna keep it like that for now. And that's gonna be times second partial of T over and then this is at dynamic viscosity, not kinematic, dynamic, over that phi Cp. And that's going to be times dCu over d sub y squared. And this right here, that is called viscous dissipation, which basically only really occurs at high velocities, but we're going to assume it's here in this case. Just because it's in the problem, and I don't know. Alright, here's the boundary conditions at y equals 0. You see that TW, this is the temperature of that sponge. So basically, oh my god. T, because we're not talking about T now, is going to be equal to T sub W, which is at temperature at the wall. That's what it means, temperature at the wall. And then at y approaching infinity, which means past that boundary layer again. You guessed it. Can you guess it? T is going to be equal to that T infinity, that room temperature. And that's all the boundary conditions. This is the first part of the problem. All right. From here, from these boundary conditions, stuff can be done, okay? This is u, by the way. This is not v. D sub u over d sub y. D sub u over d sub x. If it was d sub v over d sub y, this would be 0. Because in this problem, this is what this basically says. So that would be 0. But it's d sub u over d sub y, by the way. Partial u, partial y. Okay, from that, and from this condition right here, which is very helpful, we were able to plug that into here, and we can also plug it in right here, because you see that V again is right there. You can plug it in, V sub O, negative. That's going to help with the second part. So, from here, you can actually solve for the temperature or the velocity distribution. So I'm just gonna pull this baby up a little bit more. So this is equation 2. And this is equation 3. Alright. From equation 2. Again, we have minus v sub o over partial u over partial y. Equals dynamic or kinematic viscosity over. This is viscous dissipation. Which really only occurs at high speeds. At the wall. Okay. We can solve, because you see there's d sub u, d sub y. You're going to divide the viscosity and add this over to the other side. So you're going to get it's going to be basically a simple quadratic equation. Basically, this is the same as y squared. Well, let me write it out first. This is the rate of suctioning over viscosity, kinematic viscosity. D sub u. This is the same as writing this out. Y plus v sub o over viscosity equals 0. That's the same as this. But you got to solve it for a differential equation, so it's a little bit more confusing than that. So, for differential equations, basically when something like this, you know that this is a solution to it. So for a solution for a differential problem, u, which is u sub y, it's the thing we're trying to find, is going to be equal to c1, which is a constant, plus c2 times the exponential of minus v sub o over viscosity y. So for a differential equation when it's something like this, that's kind of the format of it. It's if this was like, if there was another term, or if this was to the third, it'd be c1 plus c2 plus c3 e to that. Or if there happened to be another solution instead of this, you would have c sub 1 e to the one solution plus c sub 2 e to the other solution, to the negative. Negative whatever. If this was minus, it'd be positive. So, with these boundary conditions for momentum, we can find C1 and C2. We're going to apply these boundary conditions, which basically say at y equals 0, u equals u infinity. So that's u infinity equals, this is going to be just equal to 1 because y is going to be 0, equals c2 plus c1. Is that correct? No, it's actually not correct. Wrong boundary condition. This one. This is at x equals 0, it only equals that. It's not y. At x equals 0. If it was y equals 0, it can mean anywhere on here. This is another y equals 0. So y equals 0. This is 0. So C1 equals minus C2. And applying this one for infinity, this is going to be just 0. Or this whole thing is going to be 0. Because anything to infinity is just 0. You just get that shit out of here. Anything to the infinity, you just fucking get that shit out of there. So, C1's going to be equal to U infinity from that. And C2 is going to equal minus U infinity. So, this is the first equation. U sub y equals you can just factor out U infinity. E exponential to the minus V sub O over viscosity, kinematic, times y, minus 1. That's the first equation. Boom! We're going to call this equation 4. From energy, we're going to use this again for the energy. As you can see, d sub d sub u over d sub y, which is this. This should be small u, but it's whatever. We can use that squared. Let's just do that real quick. What is the partial of u over the partial of y for this? That's going to be equal to minus v sub o u sub infinity over viscosity times e to the minus v sub o over viscosity y. Because that the other one's going to just cancel out, because if you're doing a derivative, there's only one derivative. If you don't even have to do a partial. There's really only one variable, so it's just a regular derivative. So that's going to cancel out the u infinity, negative 1. So exponential to a derivative is just minus that velocity, suction velocity, over kinematic viscosity times this, and then this doesn't change for exponential ones. So it's kind of easy for exponentials. So that's what we're going to use for this. Plugging 3 with this. Honestly, I should call this one 4. Plugging this into this and canceling out with the large X, this also equals 0. So you can cancel out this. It's kind of going to be the same thing as before, but it's a little bit more complex because there's just a lot more terms. On this, we only had to just divide the viscosity kinematic, and so just this over this. This, we have this term, and we have this term. So it's going to be a bit more hectic. This is just called alpha, though. But still. This is technically kinematic viscosity equals mu over phi. So you could really just say viscosity over Cp. I don't know if we're going to do that. I think we're going to just keep it like this, but... Did I do that in mine? Let me check. This one's actually really more complex for the temperature, because you got to do a partial solution and a general solution, which is part of differential equations, and add them up. Yeah, in mine I did put viscosity. So we're just gonna cancel this out. We're gonna just do this. So plugging equation 4 into 3, you get minus v sub O this is alpha, talked about before. And this is just viscosity kinematic over Cp. Times this squared. So this would be v sub O squared, u infinity squared, and that's the reason why I used it. It's because one of these can cancel out that one, which kind of helps. And this will just be 2 times that one, so it's going to be this minus 2 v sub O. Okay. So then the reason why there's a partial is because this is the equivalent of, we're going to divide out again the alpha, so it's going to be v sub O over alpha, and then this Cp times viscosity times alpha. want to see if I'm missing something. I'm... Ugh. Okay. Yeah. Alright. So, there's going to be two solutions for this. The first one, we're excluding this one. And the second one, we're just including this one. And we add them together. So for the first one, it's going to be kind of like just like we're solving this one. So the general solution, that's what it's called, is going to be just, you divide alpha, so it's going to be C3, because we already have a C2 and C1, plus C4 times exponential of minus v sub a over that alpha times y. Okay. And we could solve these boundary conditions pretty quick, but we're going to wait till we have the full solution to do that. The partial, this one's going to be a bit more complex, is a, it's just a constant a that we're going to find, times e sub minus 2, which is this, it's just minus 2 v sub o over viscosity. Wow. So, what we're going to have to do is we're going to plug this, we're going to do a partial of this, and then two partials of it, and plug them in here and here, and find a, basically. And that will give us the full solution. So easy enough, partial t sub p over partial y. It's just going to be minus 2 v sub o a over viscosity. And then e sub that term. Blah, 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 y. But this is graduate level math. You probably will not understand most of this. 2 v sub o. You probably don't even see like the actual. This is the starting stuff. This is like the problem statement. V sub o. It's just helped me study. And I find this really helps when I do it like this. I haven't done one of these sessions in a while. And basically, this partial or derivative of t sub p over y squared is just going to be, just multiply this by this. It's going to be 8 times 4 v sub o squared. Okay. So t squared fucking god. Alright, 1 second. This is just a second derivative. This is going to be equal to 4 v sub O squared, which is the rate at which we're suctioning out that fluid out of the sponge, times viscosity squared. And then the e to that value. We're going to call these 5 and 6, equation 5 here, and equation 6. We're going to plug those in to equation 3, which is the energy. So plugging that into there, this and this into that and that. I want to see if I'm doing this right again. I need to fact check myself. Yeah. Cool. Okay. So plugging this all into there, you're gonna get 2 v sub O squared A over viscosity equals alpha times this one squared. I forgot to add the exponential for this one. Well, this one's by that exponential or whatever. And that's that same term right here. Plus another v sub O squared times u infinity over Cp, viscosity times Cp, to that e to the minus 2 v sub O over viscosity. Wow. And then basically you solve for A here. This one also A. So it's A times this. And that will give us a partial solution for this. So when you solve for A, you are going to get so you subtract this from this. You're going to have to multiply the top by viscosity. Just basic, you know, fraction rules. You got to have the denominators match. So you got to multiply this one by viscosity. And this also has viscosity right here. And you're going to be flipping. Let me actually do this step by step. So when you subtract these two together, you're going to get 2 V sub O squared. I'm going to just put A right here. Viscosity minus 4 V sub O squared alpha. And this is all divided by viscosity squared. And then to that E value. The minus 2 V sub O over viscosity Y. And this is going to cancel out because this also has this value because it's equal to that right there. So the E's are going to cancel out. One of the viscosities is going to cancel out because this also has viscosity. So A is going to equal actually viscosities don't cancel out. Viscosities don't cancel out. It's going to be U infinity squared. I forgot to put a square here. It's right there. U infinity squared times viscosity squared times CP. Let me fact check that. Viscosity squared over 4 alpha Oh, the Visa O's also cancel, by the way. Because it's also in this, and you can factor out the Visa O and factor that out and cancel it. This is minus 4 alpha plus 2. Oh, wait. This is times viscosity. Plus 2 times This is the only part of the problem I'm really rough with. Okay. So, this is what the actual solution is. I'm going to try to understand it. So, again, viscosity equals that, and alpha equals K over phi Cp. And I think it also equals something with mu. Because, you know, well, this is what you're supposed to get out of it. You're supposed to get u infinity squared, of course. But you get that dynamic viscosity again, which has something to do with this phi in the problem, this from the alpha. Because alpha's nowhere to be seen in this. So basically it's just a reconstruction of the alpha, probably factoring out the K. And it's 2 mu Cp minus 4K. That's what's factored out to be. And there's probably like a reconstruction you can do to get that. But that's... Okay, so I think this is it. So viscosity over alpha is equal to parental number, which we have here. Viscosity over alpha, which is equal to mu mu Cp over K, which is what we have here, basically. So before, we had alpha times viscosity, which is equal basically this was multiplied by 1 over parental, I'm gonna guess, to get this. Because if we were to solve this realistically, we would get, these would cancel out. Oh my god. So it'd be 4 alpha So 4 alpha divided by viscosity. It'd be K over mu Cp. If it was the other way around. So I'm gonna guess the entire thing was multiplied by mu Cp, because the 2 is going to be multiplied by just viscosity. Yeah. This was multiplied by 1 over Prandtl number to get here. So let me write out what the denominator would be. Again. So it's 2 viscosity minus 4 alpha viscosity. Or no, just 4 alpha. Oh, just 4 alpha. Times Cp. Wait. The top is just mu. When it should be viscosity times viscosity squared times maybe the top and bottom were multiplied by these are both multiplied by Cp, right? Because of Cp down here. So 1 over Prandtl would just equal there's something I'm missing. This is probably the only part that I'm like I need to figure this out, or this is essential that I need to figure this out, because I could ask him, but I don't think he's gonna tell me. So Cp in the problem, it has phi C viscosity over. Wait, maybe we're supposed to expand it out. Because this is viscosity on top of here. They're supposed to be, right? Mu over Cp. It should be... Oh! That's alpha. Wait. That's Prandtl number. No. No, it's not Prandtl number. Viscosity on mine. This is what we're supposed to get, though. This is the final. It should be just V sub O squared over CP. Because you could just cancel out that. So I'm gonna guess it's just U infinity squared times V sub O squared over CP. Which is what I have. And that'd be 4 V sub O squared over viscosity squared. Oh, they're all added to each other. And V sub O squared again. So the V sub O's cancel again. And so it's alpha 2 alpha, no, 4 alpha, which is what I have, plus or minus 2 over viscosity squared. Both over viscosity squared. Wait. No, 2 viscosity. You just get a... Yes. So 2 viscosity over viscosity squared. Two viscosity. I gotta write this out because it helps a little bit too. 2 viscosity. Minus 4 alpha over viscosity squared equals, it's going to be U infinity squared over CP. There's so much fucking factoring and shit you gotta do to simplify that down to that. Really. Okay. Alright. Basically, you just simplify all the terms, I'm gonna guess. So, viscosity squared is just mu squared over phi squared.
infinity times viscosity squared over 2 viscosity minus 4 alpha.
That's what he should have, but he has it simplified down to whatever this is. Which, I mean, I know Prandtl number is mu over Cp over K. And we know that alpha equals K over phi Cp, and then viscosity equals mu over density. So I'm gonna guess it multiplies by mu Cp, or does it multiply this entire equation by Prandtl number? Because if you do that, no, that wouldn't make sense.
All right, let's expand it out. So u infinity equals, or u infinity times mu squared over phi squared over 2 mu squared over, or no, 2 mu over phi minus 4 times k over phi Cp.
Oh, it's all multiplied by Cp.
So it's mu Cp over just okay. I see it now.
I see it. Okay. So basically, this expanded out equals 2 mu Cp over phi minus 4 k over phi. So, basically the bottom just factors out. Since density's constant, you just cancel that shit out. So that's how you get the bottom. The top is viscosity. Is it just viscosity, or is it viscosity squared? Because if it's just viscosity, then it would just be mu if you just cancel out all the phis. Because, but I have viscosity squared on mine. Is there a viscosity on? Wait. Oh, there is. This is viscosity right here. Oh shit. There's a viscosity in the denominator. Okay. So this right here is viscosity times Cp. Wait. No. Yes. Yes. So this viscosity will cancel out with one of these. So it would just be viscosity on the top. And the ph's just cancel out. Okay. So basically, it just factored out density out of the entire thing. And I was just thinking that it was viscosity squared on top, but I misremembered that this was in the denominator. Okay. Boom. All right. So, with that, I'm just gonna write over here. T is the solution. You're gonna
add the partial, which is you just put in this a here, right there. That's the partial. T solution is going to be T sub G plus T sub P. And from that, when you combine them, you just solve for the... This is T sub Y. And you solve for the boundary conditions. And it gets a little bit hectic with that. A lot of simplifying is done. I'm gonna start a new page and do this. Okay. Alright, so T sub Y is going to equal C3 plus C4 e to the minus V sub O over alpha Y. And that's going to be added with that solution we got from before times the partial, which is U infinity squared times mu over 2 mu CP minus 4K. And again, we got that from just... Oh, wait. Oh, the CP's cancel out, though. The CP's canceled out. Yeah. The CP canceled out from the denominator because you multiplied this by this. So CP canceled out in the denominator, so it's just K over phi. Okay. Yeah. Okay. And this is all multiplied by E to the minus 2 V sub O over viscosity times Y. Alright, and applying both the boundary conditions at Y equals 0 equals T sub W, so it's going to be T sub W minus U infinity mu over 2 mu CP minus 4K equals C3 which C3 you can get from the other boundary condition, so let me just write that. These are both going to be 0 from the other one. From the Y equals infinity. these are gonna both cancel out because if it's anything to infinity, you just go get that shit out of here. Get that shit out of here. So cancel out both these. So just C3 from that you get equals T infinity, which is a room temperature. So with that in mind, put that in there. Equals C4. Boom shakalaka. There you go. That's T sub y. As you can see, we're almost at 2 hours now, and we are almost finished with part A. So it's a very, very, very long problem. Very long problem. We're almost done, though. Almost done. We are almost done. Now, this is something that's just in the problem, but this value approaches 1 . It approaches 1 or approaches 0. Does it approach 1 or 0? It approaches 1. As it approaches wall. So it could be neglected. Now let's talk about that a bit more. So near the wall, that equals or approaches 1. So the last term could be neglected from that. Because it's going to be really fucking small. Because you're going to be... If I... do this back out... This is what this is going to equal. So T sub y... equals... T is infinity plus T sub w minus T is infinity times that e to the VO over alpha and then it's plus, and from this we got E so that could be done. Oh! Yeah. Wait. So C4 is this minus this. So technically, this is what it should be. That last term. Times, oh wait. Well, I'll just do it like this, yeah. U infinity squared times mu over 2 mu CP minus 4K times, because you factor out this from this, and you get east of minus VO over, wait, would it be minus alpha over 2 v sub O? And then plus 1 or minus 1? Is that correct? It's times viscosity. I am so baffled. What the hell? How do you? So basically, I'm just gonna think of it this way. You can factor some value from this equation because technically this is supposed to be multiplied by this, which includes this term, but you factor it out because it also is multiplied by this term. You can factor it out over here, which is what the solution is. And I'm just gonna assume you factor it out somehow, and then this all just gets taken out because you just neglect it. It's negligible. So somehow you're able to, you know, factor these two values together, and you just cancel it out. So that's how that's done. So then the final solution, this is for the temperature distribution on the wall. T infinity plus T temperature on the wall, which is like the sponge, times T infinity, the room temperature. And it's going to be exponential of V sub O over temperature dissociativity or whatever. And that time Y. Boom shakalaka. Ugh! Such a long goddamn problem. So this is the work we had to do to get to there. And we also got the velocity distribution. That one's a lot quicker. Temperature's a bit more hectic. From here, let's go back to the actual problem statement. From here, we still have to do B and C. That was just part A. That was just part A of the problem. We could honestly just do part B and C right here, actually. B and C is really short. So again, u sub y equals, what was u sub y again? U infinity times, what do we get? Yes. V sub O over viscosity Y minus 1 that's the velocity distribution, and the temperature distribution is T sub infinity, wait, yeah, plus what we just wrote out. But this one is E exponential of the minus V sub O over alpha Y. Okay. So with these two, we could solve parts B and C pretty damn quick. So for part B, we're trying to find the local friction coefficient, which is Cf of x. And that is just this tau sub W over 0.5 phi Cp. And so you could solve this one pretty easily. You just plug in 0 for, oh god, for this, which was the value we got from before for the partial derivative of u over y. You plug in 0 here, and you get wrong one. We know that tau sub W, I'm just going to write it up. That's going to be equal to U infinity V sub O over viscosity times mu. Right? Yes. But what's mu over viscosity? Mu over viscosity is density. Because viscosity equals mu over density. So you can cancel out the mu. So this is equal to minus u infinity V sub O. Oh, it's behind my camera. V sub O times density. Who am I talking to? I'm talking to you, whoever's here. You, I guess, now. Max, how you doing? Been a while. So you just plug that into here. Oh my god. Yeah, this is the problem for my exam, but it's the opposite of this. It's injection. It's really long. I mean, it's kind of short if I don't have to explain everything, because I've been explaining a lot and trying to just... Basically, I did this in the past once before for a few of my college classes before I got, to GeoGuessr, and it really helped me study just because I was like talking it out, and it helped me just, understand it more. So that's what I'm doing it. And I will say this helped a lot. I feel like I understand this problem a lot more. So this is the local heat transfer or friction coefficient. Plugging that in, you're gonna get 2 minus 2 u infinity. The fees are gonna cancel out, so it's just CP. Right? It's d u infinity. Yeah. Oh, it's positive. It's positive. This is negative. And this is, it's not CP, it's divided by U infinity. I'm a fucking dumbass. So it's 2, and it's use infinity. I think there's a typo in the problem. I think there is. I can show what I'm looking off of. So, in the problem, he has tau of W equals phi u sub infinity v sub O, but then divides it by 0.5 phi u sub infinity. So, this doesn't make any sense because these should cancel out. So it should just be 2 v sub O. Not this. Yeah. I think it's a typo. It's gotta be. It should be just 2 v sub O. Which is kind of convenient. The other one is found from heat transfer, because it's you're trying to find H. This is the heat transfer coefficient, H of X. So Q prime of X is equal to H of X times T sub W minus T sub infinity, which equals minus K d sub T over d sub Y at y equals 0. So going back to this, we can do the partial of this according to y, and it'd be minus v sub O over alpha alpha equals K over rho CP. So you could cancel out this K. So that'd be V sub O times rho CP. And T sub W minus T sub infinity. And then these cancel out. So therefore, h of x equals V sub O rho CP. Oh my fucking god. That's it. That long ass problem. Very long. We did a lot to get there. Boom. We had to derive all these equations, cancel out what we needed to, write boundary conditions. From those boundary conditions and from what's given, we were able to find this, which helped find, with simple math, find velocity distribution. From that, we got the derivative of this, which we could help find the temperature distribution, and this one squaring it. And from that, we got a general and partial, and from the partial, we plugged the partial into the energy, did the partial, or the derivative of according to y, and solved for a. And from that a, we plugged it into the partial, which from that, we went and we added both of, wait a minute. We added both of those up, because the partial plus the general equals the full solution. And then from that, we applied the boundary conditions from the energy, this right here. And we found the constants. And then from that, we made this assumption that it could be neglected, this one, because it approaches 1. Don't know exactly fucking why. And we also canceled out this from C4 and from the partial because of that. So then we got this simple, nice looking solution. And from both of those, we got the local friction coefficient and the local heat transfer coefficient from just simple math. From using the heat transfer rate correlation and using the shear stress and simplifying that. I do think there is a typo though. There's no, that just doesn't make sense. This doesn't make sense. How can you get 2 rho VO over U infinity from this? It's 1/2 phi over U infinity. Unless it's just 1/2 phi. Wait, that wouldn't still make sense either. Yeah. I still don't know. I really still don't know. I'm gonna email my professor about that. See if there's a typo there. I'm also gonna ask him maybe more information on how this can be neglected and how C4 was able to get canceled out there. What needs to be done? Because it did not have this value. It has alpha as the denominator. Because if you multiply C4 there, it should have that. Like if you go here, it says C4 times this. C4 times this. C4 equals this. Yet, it's not multiple. The denominator is not alpha here. It's viscosity for some reason. Oh, wait.
What does that say? It says VO times something. What in the hell is that?
Oh my god. Wait a minute. Beta over alpha. Oh, yeah. Okay. So yeah, that's that. That's the solution. Oh my god. Took a fucking millennium, but we did it. I am exhausted after that. You can see how I fucking spend a majority of my day doing this shit. It really is long. It really is. Okay. I think I'm gonna call it there. I'm not gonna save that. Okay. I will see you guys maybe later today. I'm going to take a break and maybe go for a run, and then we'll see how I feel after that. Anyways, boys, peace out. I'll see ya. Deuces. Peace out.